In this video, we're going to prove some identities involving inverse trigonometric functions. Here's one of them. Prove that tan inverse root x is equal to half of cos inverse 1 minus x by 1 plus x. And it's also given that this is true when x belongs to this set 0 to infinity. Pause the video, give this a try. Okay, let's do this together. In such scenarios, in such problems, we usually find good suitable replacements for x. If you have to simplify both the sides, we have to get rid of these inverse functions, tan inverse and cos inverse. Let's look at the left hand side. We have tan inverse root of x. Now, what should we substitute x with to get rid of the root as well as tan inverse? Think about it. Okay, so this has to be a square and it has to do something with tan. We can substitute x as tan square theta. If we replace x as tan square theta on the left hand side, this is what we get. We get tan inverse root of tan square theta. Root and square cancel out. This becomes tan inverse tan of theta, which becomes theta. So this is the left hand side. Pretty neat. What's the right hand side? Here we have half of cos inverse 1 minus tan square theta by 1 plus tan square theta. And this is an identity. 1 minus tan square theta by 1 plus tan square theta. That's actually cos of 2 theta. So we can rewrite this. This is half of cos inverse cos of 2 theta. Again, cancelling cos inverse and cos, we get 2 theta by 2. That's equal to theta. So both sides end up being theta, which means both sides are equal. Hence, we have proved that this identity works. But in this video, we'll dive a little deeper and talk about this range as well. X belongs to 0 to infinity. Where does this come from? Can we make sense of this? Alright. So, can we really cancel tan inverse and tan without worrying about theta? Well, no. We can only do this when theta lies in the principal value branch of tan inverse. And here as well, we can only cancel cos inverse and cos if 2 theta lies in the principal value branch of cos inverse. This gives us some constraints. So if theta lies in the principal value branch of tan inverse, this means theta belongs to these two quadrants, 4th and 1st. Theta belongs to minus pi by 2 to pi by 2. And here we get the constraint 2 theta belongs to this set 0 to pi. This is the principal value branch for cos inverse. If we divide by 2, we get theta belongs to 0 to pi by 2. Now we are doing both of these, which means theta satisfies both of these conditions. So if we take the intersection, we get that theta belongs to 0 to pi by 2, the first quadrant. And when theta is in the first quadrant, what's happening with x? X is tan square theta. Tan square 0 is 0 and tan square pi by 2 will be approaching infinity. So x belongs to 0 to infinity, this set. So this is where this set is coming from. But that's not all. There are more constraints. This x is inside the square root function. So this means this x has to be greater than or equal to 0. That's another constraint. Also, tan inverse and cos inverse have their own domains, their own valid values that you can input. Tan inverse has a domain R. So you can input all real values, which doesn't give us anything, but it's good to write this down. Cos inverse has the domain minus 1 to 1. You can only input values that are in this range, minus 1 to 1. So that's another constraint. 1 minus x by 1 plus x that we're inputting here, that has to be within this range, minus 1 to 1. So let's see what this gives us. Here we can say that 1 plus x, the denominator, will be always positive because x is also satisfying these other constraints. Here x is greater than or equal to 0, x is greater than or equal to 0. So when that's the case, the denominator is always positive. And if the denominator is positive, we can cross multiply. This is minus 1 times 1 plus x less than or equal to 1 minus x less than or equal to 1 plus x. If we simplify this, we get this double inequality. If we take the first part of it, minus 1 minus x less than or equal to 1 minus x. Cancelling x out, we get minus 1 less than or equal to 1. That's always true. So we get no new information. But what about this other side? We have 1 minus x less than or equal to 1 plus x. Here 1 will cancel out. 2x is greater than or equal to 0 or x is greater than or equal to 0. Now, usually this constraint is written in the question itself and we don't have to worry. We don't have to bother about where this comes from. But it's good to pause and reflect every once in a while and look at what's happening behind the scenes to get to this constraint. Let's solve another problem. Prove that cot inverse root 1 plus sine x plus root 1 minus sine x, that's the numerator, divided by root 1 plus sin x minus root 1 minus sin x, that's the denominator. Prove that this is equal to x by 2 when x belongs to this set 0 to pi by 4. Pause the video, think about it. Okay, what substitutions should we use to simplify the left hand side? We have 1 plus sin x and 1 minus sin x both inside the square roots, which means both of them have to be perfect squares. How can we make them perfect squares? Well, here's the substitution. We can replace 1 with sin square x by 2 plus cos square x by 2. 1 is equal to sin square plus cos square. Now we have a square plus b square. We need 2ab or minus 2ab. That's something that we can get from sin x. Sin x is equal to 2 sin x by 2 cos x by 2. Now 1 plus sin x becomes sin x by 2 plus cos x by 2 whole squared. And 1 minus sin x, that becomes sin x by 2 minus cos x by 2 whole squared. A plus b squared and a minus b squared. This means root 1 plus sin x, that's equal to sin x by 2 plus cos x by 2. And root 1 minus sin x, that's equal to cos x by 2 minus sin x by 2. Notice we have written cos minus sin because we're in the first quadrant. This constraint says we're in 0 to pi by 4. When you half this, you're in 0 to pi by 8. That's still the first quadrant. And in this range, cos is greater than sin. When you're less than pi by 8, when you're between 0 and pi by 8, your cos will be greater than sin. And because you're taking the square root, you will always output something positive. If we switch this, if we write this as sin minus cos, this will come out to be negative in this range. That will not work. Let's move forward. If we replace these values here, we get sin plus cos minus sin. And the denominator is sin plus cos plus sin. So the numerator simplifies to sin cancels. This is 2 cos x by 2. The denominator is, here we have cos cancelling out. We have 2 sin x by 2. 2 cancels out. Cos by sin is cot x by 2. So all of this is equal to cot x by 2. Which means if we take cot inverse of this, we should get cot inverse of cot x by 2. That's equal to x by 2. Again, a quick reflection of why this range is important, why this constraint is important. If we take x outside this range, let's say we take x more than pi by 2 outside the first quadrant, in that scenario, root of 1 minus sin x, that becomes sin x by 2 minus cos x by 2. Because when you half this, you're more than pi by 4. And for values more than pi by 4, we have cos less than sin, which means if we want the positive output, we'll have to write this as sin minus cos. And this changes everything. Now when you plug this back, you will not get cot x by 2. You'll get a different expression. Let's move on to the next one. Prove that tan inverse root 1 plus x minus root 1 minus x divided by root 1 plus x plus root 1 minus x, that's equal to pi by 4 minus half cos inverse x, and x is in this range. Pause the video, think about it. Okay, now what substitutions should we use here to simplify the left hand side? We have 1 plus x and 1 minus x in the square root. What can x be so that we can have both of these as squares? 1 plus x is a perfect square and 1 minus x is a perfect square. Alright, here's the answer. X is equal to cos of 2 theta. That's the substitution that we'll use. Cos 2 theta can be expanded in two ways. We can write this as 2 cos square theta minus 1 or 1 minus 2 sin square theta. Now when we use these two, we'll get 1 plus x and 1 minus x, both of them as perfect squares. 1 plus x will be 2 cos square theta. 1 minus x will be 2 sin square theta. So root of 1 plus x, that's going to be root 2 cos theta, taking the square root, and root 1 minus x, that's going to be root 2 sin theta, again taking the square root. Now let's plug these values here. We have root this minus this by root this plus this. So we have root 2 cos theta minus root 2 sin theta divided by root 2 cos theta plus root 2 sin theta. We can take the root 2 common and cancel out. We have cos theta minus sin theta by cos theta plus sin theta. We're not done yet. We need this in the form of tan because we want to cancel tan inverse. That's good progress. Now how can we convert this in tan? Pause the video, think about it. Okay, here we can use yet another identity. We can use tan A minus tan B by 1 plus tan A tan B. That's equal to tan of A minus B. Here A is pi by 4, tan pi by 4 is 1. So tan pi by 4 minus tan theta by 1 plus tan pi by 4 times tan theta. That becomes tan pi by 4 minus theta. Now we're ready to cancel. Taking tan inverse of all of this, that becomes tan inverse of tan of pi by 4 minus theta. Tan inverse and tan cancel out. We have pi by 4 minus theta. And what's theta? X is equal to cos 2 theta. So if we take cos inverse, we have cos inverse x equals to 2 theta, which means theta is half of cos inverse x. So we can plug this here. This becomes pi by 4 minus half of cos inverse x. And this is the right hand side. Hence we have proved what we wanted to prove. Let's see where theta belongs. Theta is half of cos inverse x. So that's half of cos inverse minus 1 by root 2 to half of cos inverse 1. Cos inverse minus 1 by root 2. Cos inverse has first and second quadrant. Negative value, which means we're in the second quadrant. 1 by root 2, which means it's pi by 4, 3 pi by 4. So theta belongs to 3 pi by 8 because we're taking half. 3 pi by 8 to half of cos inverse 1. Cos inverse 1 is 0. So that's 0. This is greater than this. So we can flip it. Theta belongs to 0 to 3 pi by 8. That's the range. Let's check if all of these things work for this range. When theta is in this set, 0 to 3 pi by 8, we can comfortably take the square root and write root 2 cos theta. We're in the first quadrant and cos theta is positive. We can do the same here. We can write root 2 sin theta. Sin theta is positive. What about this value? Pi by 4 minus half cos inverse x. That's pi by 4 minus theta. So this is greater than or equal to 0 and this is greater than or equal to 0 in the first quadrant. So these square roots don't have a problem. What about this value? Pi by 4 minus theta. Let's check that as well. Theta is from 0 to 3 pi by 8. So 0 less than or equal to theta is less than or equal to 3 pi by 8. Subtracting pi by 4 from all three sides, we have minus pi by 4 is less than or equal to theta minus pi by 4 is less than or equal to 3 pi by 8 minus pi by 4. This becomes minus pi by 4 less than or equal to theta minus pi by 4 less than or equal to, taking 8 as the LCM, we have 3 minus 2, that's 1. So pi by 8. Now flipping the sign, we have pi by 4 minus theta. That's from minus pi by 8 to pi by 4. And this also works. This is well within the range of tan inverse. That's the first quadrant and fourth quadrant, minus pi by 2 to pi by 2. This value is within that range, minus pi by 2 to pi by 2. So this also works. We can cancel this out when x belongs to this set.